So far in our study of logic, we have learned that a statement is a sentence that is either true or false. We also recognized that some statements can be quantified. That is, they contain words like all, some, and no. In section 3.2, we'll examine compound statements and connectives. So for now, we're going to leave the quantifiers behind and deal with simple statements. We need to examine how simple statements are connected to understand their meaning. Section 3.2.1 concerns compound statements. Definition: a compound statement is formed by combining two or more simple statements using the connectives and, or, if then, and if and only if. Now, each of these connecting words has a symbol and has the symbol that looks like a hat or has the symbol that looks like a V. The phrase if then is represented by a one direction arrow, and the phrase if and only if has a two direction arrow. Also, sometimes in math books, you will see if and only if abbreviated as IFF. We now proceed to examine each of these connectives individually. We'll begin with conjunctions. Keep in mind, a logical conjunction is not necessarily the same thing as a conjunction in the English language, so pay attention and watch for the difference. Definition: the statement P and Q. Now remember, P represents a simple statement and Q represents a simple statement, each of which will have some sort of truth value, either true or false. So when I join those two statements with the word and, we call it a conjunction. We symbolize this such as P and Q. This is called a conjunction. So specifically in a logical statement, two simple statements joined by the word and, only and, is a conjunction. There are other words in the English language that are classified as conjunctions as far as grammar goes, and, or, but as far as logical statements go, a logical conjunction is two statements connected by the word and. In example 1, you may get a glimpse of how we can take an English statement and convert it into symbolic form. And through this, you will begin to develop an intuition on how we call math another language and how English or any other language is actually an expression of mathematics. So use the given simple statements to translate the symbolic form to word statements. So we're going to deal with two simple statements. P will represent the statement, coffee contains caffeine. And Q will represent the simple statement, coffee contains antioxidants. Both of those are logical statements and they have a truth value. We're going to translate the symbolic form P and Q, which is very concise, into its English equivalent. So we'll begin with the statement P. Coffee contains caffeine. So that's the P part of our symbolic statement. The next thing that I see is this symbol, and we have learned that represents the word and. Then we'll translate the statement Q. The statement Q is coffee contains antioxidants. Now, it's not absolutely necessary to write the entire statement to correctly translate the symbolic form. I can shorten it. English language gives us that freedom. We can simply say and antioxidants. Now, it would still be correct to write coffee contains caffeine, comma, and coffee contains antioxidants. That would be a correct English translation of the symbolic form over here. But again, coffee contains caffeine and antioxidants is a sufficient translation of that symbolic form. Let's try the next example. The statement is P and, remember, this symbol represents a negation. So this is the statement P and not Q. So to translate this into words, I'm going to start with statement P, which is again, coffee contains caffeine. The next symbol that I see here represents the word and. Then I have to form the negation of the statement Q. The statement Q is coffee contains antioxidants. Notice there are no quantifiers, all, some, and no, so we can negate this statement simply by inserting the word not. So we will say coffee contains caffeine and not antioxidants. Okay, it would also be equivalent to say coffee contains caffeine but not antioxidants. When I read that statement in English, I would translate it using this symbolic form. Another possible variation would go something like this. Coffee contains caffeine, comma, but coffee does not contain antioxidants. So we're making this concise with the freedoms afforded by the English language. Now, one thing I also want to point out here, we're learning the conjunction, which is connected with the word and if you can associate this symbol with the intersection symbol, remember we learned in the previous chapter about the intersection of two sets. It's what those two sets have in common. And the intersection symbol looks like an upside down U, and it goes with the word and. Here we have a symbol that is an upside down V. That is used for the word and when we are dealing with logical statements, not sets. But you can see that both of those symbols face in the same direction. That's also going to apply to disjunction. Part B, we'll talk about another connective dealing with a disjunction. Definition. The statement P or Q denoted, we read this P or Q, is called a disjunction. Now keep in mind, in the English language, the words and or are both classified as a conjunction. However, in logic, and is called a conjunction and or is called a disjunction. There's going to be a difference in their meaning. Now, just like we associated the symbol for and with the intersection from set theory, we can associate the symbol for or with union from set theory. Remember, when we're finding the union of two sets, union corresponds to the word or. The union symbol and the logical symbol for or point in the same direction. If you can associate these new symbols with logic, with what you've learned about set theory, it'll help reinforce your understanding. Let's try example 2. Use the given simple statements to translate the symbolic form to word statements. Let P represent the simple statement, the motion receives a unanimous vote, and Q represents the motion is carried. We want to translate the symbolic statement P or Q into words. So we'll start with the statement P. The motion receives a unanimous vote. Then we'll translate this symbol for or and include the statement Q. The motion is carried. Or the motion is carried. Now, to be grammatically correct, I'm going to need a comma right there. Another possible translation, if we wanted to shorten a little bit and get rid of the comma, we could say the motion receives a unanimous vote or is carried. That would also be correct. Let's try the next symbolic statement. We read this P or not Q. So again, we're going to begin with the simple statement P. The motion receives a unanimous vote. Then the connective here is the word or, and then we need to form the negation of Q. Since Q does not contain a quantifier, we can negate it simply by inserting the word not. Or the motion is not carried. So looking at our English translation here, we have the motion receives a unanimous vote. That is the statement P. Then we have the disjunction or, represented by this symbol. We have the motion is carried, that's statement Q, And this word not is the translation of the negation. So each symbol represents a phrase or a connective, and so we can translate it into an English statement. So a conjunction is two simple statements connected by the word and a disjunction is two simple statements connected by the word or. The question is, when is a compound statement true? When is a compound statement false? After we get a comfort level of translating symbolic statements, we'll learn how to determine when is a compound statement true or false. Let's look at another important connective. This one's used all the time in mathematical theorems. It's called a conditional. Definition: the statement, if P then Q, denoted P arrow Q, is called a conditional. You may have heard a mathematical theorem stated as a conditional. If P then Q. We could also read this, P implies Q. The statement P at the beginning of the conditional is called the hypothesis of the conditional. And the statement Q at the end of the arrow is called the conclusion. Let's practice translating some conditionals. Example 3. Use the given simple statements to translate the symbolic form to word statements. Use your intuition to determine which of the given statements are equivalent. Now, we're going to learn a more concrete way to do this. For now, I just want you to use your intuition. Let's begin translating these statements. Suppose that P represents the simple statement, Lisa lives in Amarillo, and Q represents the simple statement, Lisa is a Texan. And we want to translate the first conditional. Now, the first statement in our conditional, the hypothesis, is P, but the conditionals begin with the word if. So we'll start with if, and then we'll write the statement P, that is, Lisa lives in Amarillo. And then we'll translate this connective as then we have Q. Then Lisa is a Texan. We could also say she is a Texan. If Lisa lives in Amarillo, then she is a Texan. The hypothesis of that conditional is statement P, Lisa lives in Amarillo. The conclusion, which is what the hypothesis implies, is Lisa is a Texan. Now, notice that the conditional arrow is a one-way street. It points from the hypothesis to the conditional, and I can't read it in the wrong direction. It would be like going the wrong way down a one-way street. So let's examine the next conditional. Q implies P. So this time, the hypothesis is going to be Q. If Lisa is a Texan, then the conclusion this time is P. She lives in Amarillo. Now compare those two conditionals. The first one says, if Lisa lives in Amarillo, then she is a Texan. That makes sense. And read the second one. If Lisa is a Texan, then she lives in Amarillo. Well, that's a possibility, but she could also live in Lubbock or Hereford or Dallas. So those two conditionals don't mean the same thing. The arrow in the conditional, again, is a one-way street. And if I try to read it backwards, if I switch the hypothesis and the conclusion, I get a logically different statement. So those two conditionals are definitely not equivalent. Let's try another variation. This one is not P implies not Q. Now remember, when I see this conditional arrow, I'm going to begin the statement with the word if. The word if identifies the hypothesis. Whatever statement follows the word if is the hypothesis of the conditional. So we need to form the statement not P. So if Lisa does not live in Amarillo, then now we need to form the statement not Q. She is not a Texan. Okay, let's try our last variation. A lot of negations in this one as well. Not Q implies not P. We'll begin our conditional with the word if. If not Q. So we need to negate the statement Q. If Lisa is not a Texan, then, now we're going to form the statement not P. Lisa does not live in Amarillo. So let's read that last conditional again. If Lisa is not a Texan, then Lisa does not live in Amarillo. That makes sense. If she's not a Texan, then she cannot live in Amarillo. So we've just gone through what's called the 4 variations of the conditional. Part A is your original conditional. Part B is the converse, which we discovered is not equivalent to the conditional. Example C is the inverse. And example D is known as the contrapositive. Now, a conditional and its contrapositive are equivalent. So notice what happens. Here in the conditional, I start with P and I end with Q. In the contrapositive, notice the order of those statements has been reversed and each statement has been negated. A conditional is equivalent to its contrapositive. Sometimes, if you give a conditional as a statement, you can clarify yourself by forming the contrapositive. It's equivalent, but it brings to light different concepts. Notice here in the converse, we've got the direction Q first, P second, and that direction has been switched here with the inverse, and both parts have been negated. So that's the same relationship that we saw with the conditional and the contrapositive. So the converse and the inverse are equivalent. If you're ever listening to a logical argument, a debate, or some sort of political discussion, and someone substitutes a converse for a conditional, you'll be able to understand that is not equivalent and that is bad logic. Or if you hear someone replace a conditional with a contrapositive, that is good logic and that is equivalent. So these variations help you to understand debates, scientific papers, statistics, articles. It helps you with logic. In fact, mathematicians are required to take classes in logic because many theorems are based on logical statements. Lawyers are required to take classes in logic. Scientists, philosophers, many that major in some sort of political science such as government or history also have to take classes in logic. So hope you find that interesting. Let's look at one more connective called the biconditional. Now the prefix bi represents 2, so a biconditional is really 2 conditionals in one. The statement P, if and only if Q, denoted, now look how this is denoted. The arrow has 2 directions. Sometimes this is also abbreviated PIFF, that means if and only if Q. This is a biconditional. It's a 2-way street, whereas a conditional is a 1-way street. Example 4. Use the given simple statements to translate the symbolic form to word statements. Let statement P represent the simple statement, the polygon is a triangle, and Q is the simple statement, the polygon has 3 sides. And we want to translate this biconditional. So unlike a conditional, which begins with the word if, a biconditional has the phrase if and only if in between its 2 simple statements. So I'm going to begin with the statement P. The polygon is a triangle. In the middle between the 2 simple statements, we'll insert the phrase if and only if, which you could also abbreviate as IFF, and we'll finish with the statement Q. The polygon has 3 sides. contrast that with the next example. The next example is a one-way conditional. And I've got a typo, sorry about that. Please correct that to P. With the one-way street, we're going to begin with the word if. If P, if the polygon is a triangle, then Q, the polygon has 3 sides. And statement C begins with Q and ends with P, and it is a conditional. It is a one-way street, so we start with the word if. If Q, if the polygon has 3 sides, then P, the polygon is a triangle. You can identify those two statements, like we did on the previous, as a conditional and its converse. Now, let's look at our last example. You ready for this one? It says, if P, then Q, and if Q, then P. Let's translate that. So we are basically translating a conjunction. Let's start with the left-hand statement. The left-hand statement is the conditional, if P, then Q. If the polygon is a triangle, then Q, it has 3 sides. Then we translate our conjunction, and this part right here is the converse, if Q then P. If the polygon has 3 sides, then it is a triangle. So we're building up to something here. We're practicing going from symbolic form to word form, but we're also doing this to make a point. We started with the biconditional, P, if and only if Q. Then we examined 2 directions of the conditional and its converse. Notice example D is the conjunction of the conditional and its converse. That's basically what the biconditional represents. The biconditional is 2 conditionals in one. It is the conditional and its converse joined together in one symbolic statement. So if you want to get really fancy, we could say the biconditional, P, if and only if Q, is equivalent to, that's a fancy equals that we use with logical statements, if P then Q and if Q then P. So we're saying the biconditional represents both directions of the conditional. Bottom line, what do you need to know? You need to know the 4 basic connectives. A conjunction is 2 simple statements connected by and. A disjunction is 2 simple statements connected by or. A conditional is a statement of the form if P then Q, and a biconditional is a statement of the form P if and only if Q. The skills that you need to acquire from this section are translating from symbolic form to word form. If you can master that, then you are well on your way to understanding this section.